In this video, we are going to explain the concept of equilibrium. There are two criteria which constitutes whether a body is in equilibrium. Firstly, that there is no resultant force, and secondly, there is no resultant moment. As a result, a body in equilibrium will not be accelerating. So it will not be changing in speed or direction. It will also not be rotating or spinning in any way. To clarify, when I say the word body, both body and object basically mean object, and it's just the thing that we are considering the motion of. So it could be like a ball, a rod, a person, a mass, a weight, all of those. To clarify what we mean by equilibrium, let's look at two examples which are not cases of equilibrium. In the left diagram, there is no resultant force, but there is a resultant moment which is acting in the clockwise direction, and so it is not in equilibrium. In the right diagram, there is no resultant moment because both of these moments cancel each other out, but there is a resultant force, and so it is not in equilibrium either. A result of the definition of equilibrium is the principle of moments. This states that the sum of the anti-clockwise moments about a point equals to the sum of the anti-clockwise moments about the same point when in equilibrium. It's very important that these are about the same point. So for example, if we consider the diagram on the right, we know that if this object is in equilibrium, the clockwise moments, which is created by this force multiplied by this distance, should be equal to the anti-clockwise moments, which is created by this force multiplied by this distance. We will now look at some examples of systems that are in equilibrium. An object with no forces acting on it will obviously be in equilibrium, as in this diagram here. The system with many forces acting on it, though, is also in equilibrium, with the blue forces canceling each other out, and then the purple forces canceling each other out, because they are acting in opposite directions. However, you can also see that there is a moment due to these forces. The blue forces cause a clockwise motion, while the purple forces cause an equal and opposite anti-clockwise motion. As a result, the moments also cancel each other out, or the couple cancels each other out. And so all the forces and moments are balanced, therefore this system is also in equilibrium. A side note that if an object is moving at constant velocity, it will also be in equilibrium, even though it is moving, which is something that people might misunderstand, because there is no resultant force or resultant moment acting on it. If it's still, however, and in equilibrium, this is sometimes referred to as a static equilibrium. So this is when an object is not moving. Another way of representing force systems is by drawing vector diagrams. If we have a coplanar forces in equilibrium, forces can be joined to form an enclosed shape. If we have three forces that act on a body, for instance, as in here where this black dot in the middle is supposed to represent a body, we can form a vector triangle. So that's the diagram here on the left. What we've done here is that we've joined the three forces, and these have to be joined head to tail. So the head of one of the forces must join with the tail of another force. The head of this force joins with the tail of this force. The head of this force joins with the tail of this force. And all of these forces will form a closed shape if they are in equilibrium. If you are wondering what coplanar forces are, this means that all the forces act in the same plane. So you can think of it as all the forces acting all on flat on the same surface, if that makes sense. Lastly, bodies can be in stable or unstable equilibrium. If a body is in stable equilibrium, it will return to its original position after it has been displaced from that position. An example would be the diagram on the left, where we've pushed this block slightly, it's moved tilted slightly to the right, but it will return to its original position. If we look at the diagram below, this idea can be further explained. When we push it to the right slightly, we have the weight of the object acting downwards, and we have this point here acting as the pivot, which is in contact with the ground. The reaction force will act upwards from the pivot because that's the only point which is touching the ground, and the weight will act downwards, obviously, because the center of mass hasn't moved. Now, what we have here is we have a perpendicular distance between the pivot and the weight. As a result, we have a moment which acts anti-clockwise, causing the object to fall back towards its original position. We also have the case of unstable equilibrium. This is when an object will not return to its original position after it has been displaced from that position. So if we look at the diagram below the first one, we can see that here the weight is acting from the center of mass, and the pivot point where the reaction force is acting up is slightly to the left of the center of mass. This causes there to be a clockwise moment which tilts the box down, and so it becomes balanced or in another stable equilibrium state where one flat surface is on the ground. So you will have seen these kinds of examples already in real life. If you try to balance the box on the one edge, it falls over very easily. If you balance it on a side, it will stay there stably. This video was created by Naproud Academy, our global online tutoring platform. If you found this video helpful, please support us to continue making more free videos by liking, commenting, and sharing. Check out our website, www.naproudacademy.org, to apply for tutoring and also to find free, useful study resources such as past papers by topic and revision notes.